Okay, welcome back uh, to this course. And let me begin this lecture by briefly reviewing what we did last lecture. In the last lecture, we actually covered a quite important step in our course by delivering a full quantum theory of the hydrogen atom. So it was a quite long and perhaps a little bit intricate, a bit of an intricate problem and approach. So let me just review what were the main ideas of it, right? And then we move one step forward and compute the ground state explicitly. So basically, all of our derivation was based by by translating into quantum mechanics the idea that we had developed for the classical theory of the hydrogen atom. So remember, in the classical theory of the hydrogen atom, we were looking at the three-dimensional Schrodinger Newton's equation. And what we did, rather than just look at Newton's equation, was to look at the kinetic energy and potential energy, mechanical energy in general. Because we wanted to take advantage as much as possible of the conservation of energy. And then by choosing carefully the coordinates, we were able to show that the kinetic energy part could split into an effective kinetic energy involving only the radial part. You see here, the vector has disappeared. The potential part also depended only on the radial part. And all of the angular motion was translated into an effective potential, which involves the classical angular momentum. Now, when we translated this approach to the quantum level, of course, we have to use a slightly, well, not slightly, quite significantly different language. And instead of the energy, of course, we look at the quantum Hamiltonian. And a quantum Hamiltonian in general, for a single electron, would be written with the Laplacian, with the Cartesian coordinates, plus a potential, and the potential would be, of course, the Coulomb potential. Now, the key observation there that was basically equivalent to this splitting of kinetic energy into two terms, here and here. The key observation was that if you go to polar coordinates, the Laplacian term translates into a term that depends only on angles, which I'll write in a different color, on this, not on angle, sorry, on the radial distance, plus a term that depends parametrically on distance, but only involves derivatives with respect to angles. And the second very important piece of information we had was that actually this part here, this angular part, is proportional to L squared, the square of the angular momentum. So combining all things together, the Hamiltonian in polar coordinates is written as h bar squared over 2m negative 1 over r d squared over dr squared r times whatever the wave function is, plus u of r plus L squared over 2nm out. So let me, before we move on, analyze a little bit better what this term here is. So let's call this t. T, what this notation means is that when I apply t to some wave function, which is a function of r, theta, and phi in general, all I have to do is to take second derivative, take 1 over r, multiply the function by r, and then take the second derivative irrespective. Okay, so I think you appreciate now that we get something very close to the overall structure we noted when we were doing the problem at the classical level. It is also quite interesting to see an important implication that, an observation has important implication is that L involves only derivatives of a theta. And this implies basically that a wave function, which is a function of r, theta, and phi, can be actually rewritten as a product of a function that depends on r times the eigenstates of the square of the angular momentum operator, which we know are the spherical harmonics. Now, based on this fact, our Schrödinger equation can be decoupled into a family of one-dimensional Schrödinger equations, depending on the value of L. So, more specifically, the complete Schrödinger equation, H psi equals E psi. Oops, maybe I should use a different color. Can be decomposed into a family of Schrödinger equations in the form negative h bar 2m 1 over r v squared dr squared r plus potential energy plus h bar squared L plus 1, but now L is a parameter, acting on the radial wave function only. So this is called a radial wave function, a radial Schrödinger equation. And this is the radial wave function. Now, once you have the radial wave function, then you basically are in shape. And you have, in other words, in order to solve for the entire spectrum, what you need to do is to, first of all, decide in which states of angular momentum you are, whether you are in the S states, in which case this term, this term here disappears for S states. So this is equal to 0 for S states. That is states for L is equal to 0. It is equal to h bar squared divided by mr squared when L is equal to 1, which are called the P states. And then there are D states and so on and so forth. And depending whether you're looking at the wave function for S states or P states, you have a different Schrödinger equation. And if you can solve this Schrödinger equation, of course, you get quantizations levels for each of these. So you will get different S states as well as different P states and different RAD states and so forth. And then if you arrange all of them in terms of the energy, and you rank them from the lowest energy to the highest energy, you discover that the ground state is a 0s state or 1s state, I think it's called. Then you have the second excited state is an S state, then you have 1p state, and so on and so forth. So, in principle, the radial wave function has been solved analytically in the first half of the last century. And this was a fantastic achievement because it allowed people to actually predict all these distances in energy, in quantization energy. And the fact of having these distances enabled the scientist to perform a very, very, very thorough evaluation of the accuracy of this equation. How? Basically by shining light of different wavelengths onto hydrogen atoms. Because the theory predicts that in order for this light to be absorbed by the hydrogen atom, the electrons must be taking the energy of the photon. So we can depict this to be proton, an electron, a photon that has arrived. And basically what the electron can do is to move to an excited state. We can represent it this way, but it's more appropriate to say that, this is a classical picture. A more appropriate picture would be I have an electron, say, in an S state, and then a photon arrives, and this photon can be absorbed and lift the electron to any of these states, for instance, in this case, to a P state. Now, since only certain energies can be absorbed, only energy corresponding to differences between two energy levels can be absorbed. And since the energy is delivered by the photon, since the energy of a photon is related to this time fixation by the usual photon relationship, it means that only certain frequencies can be absorbed. So basically what this is telling me is that, if I look at the absorption and emission spectrum, because when the electron disexcites, it can emit a photon, I expect only certain frequencies to be characterized, to be emitted or absorbed by certain atomic species. And this was crucial because you can basically demonstrate the spectrum of a hydrogen atom by looking at what frequencies are absorbed or emitted by that atom, or stated differently in a generalized sense by looking at the color of the atom. So these spectroscopy experiments were a big deal last century and actually provided a thorough verification of all these mathematical predictions, arriving to establish quantum mechanical theory as a really fundamental theory for atomic structure. So this is all extremely interesting and extremely important. One piece of information, though, that is still missing is that we do not have for this system, in principle, if you look in the literature, you find in books, you find very sophisticated derivation of the solution of the radial equation. But they're too complicated for us. So we would be happy to have just a variational estimate of the hydrogen atom ground state, for instance. So if you look in the nodes, you will find in the material which is reported in my website, you will find one link called variational calculation of H atom wave function. So basically, what is the idea? Well, the idea is to make a variational guess, and then actually we make two variational guesses, and then apply the weight variational principle. So let's do this exercise together. The first variational guess we do for the radial wave function is the following. Then the usual beloved Gaussian. So this is a normalization term. And remember, we are working in polar coordinates. So the normalization of a wave function will be integral in the d theta, d phi, sine theta, y theta, phi. I actually should call this r, not sine. Integral dr from 0 to infinity, r squared. This comes from the Jacobian of r modulo squared, right? So if you do this check, you discover that this normalization actually works. So with this normalization, my radial wave function is actually well normalized. The next step is to compute the expectation value of the Hamiltonian in this variational ansatz, and then change A, in this case, the variational parameter, until I get the smallest possible value. That would be my best guess. Now, if you look at R, the radial part of the kinetic energy, and R, and you do calculations, and you find the calculation explicitly in the notes, you discover that this would be 343 squared. Inappropriate units, I'm not using H bar, I'm just working in units where H bar is identity and the mass is 1, the atomic units. And then if you take the expectation value for the potential energy, which is a Coulomb energy, and you do the calculation, you'll discover that this will give you 2a negative root of pi. It's negative because the Coulomb energy is in fact negative. So the kinetic energy is positive and the potential energy is negative. Okay, fine. So when you sum them up, the expectation value of the energy altogether is something like 3 4a squared minus 2 over a root of pi. So if you plot it as a function of r, it looks like this. And there's in fact a minimum value, a bar. And if you find out what the minimum is, you find that a at the minimum is about 1.3, and the minimum value of the ground state, the variational estimate, will be minus 0.42 in these units. Fine, that's a first variational estimate. Is it good or is it bad? Well, let's try another one and see if I can do better or worse. Now remember, here I use the Gaussian ansatz. Let's now try another ansatz. Reasonable ansatz. And this is one in which the radial part of the wave function is 1 over root of 2a squared a cubed, and it's simply an exponential fold of the radial wave function. So again, you can use this to compute the kinetic energy, expectation value, which are called T. You can use it to compute the potential energy and sum things up. And in this variational ansatz, the result is 1 over 8a squared minus 1 over 2a. So we find something quite expected. Now, of course, this a is a dimensional parameter, and energy is a dimensional parameter in this approach because we have set all the physical units to 1, h bar, mass, and so the dimensions here are actually not the physical dimension. One should, in the end, restore the correct dimension by redoing the calculation with all the masses in h bar floating around. I'm not interested in doing that here. So to see what interesting. It is interesting, nevertheless, that the potential energy, as a structure says, okay, if A is the typical distance from the center of the nucleus of the electron, right? Then the typical potential energy is of the order of 1 over A, which is, since the potential energy is 1 over R, then clearly the typical distance, this is the typical half distance, A. That's why you get something like 1 over 2 over A. It's not a proof, it's just that it makes sense. Likewise, if A is the typical scale over which my wave function changes, I expect the typical momentum to be of the order of 1 over A. And that's why the typical kinetic energy is of the order 1 over A squared, typical momentum squared. Okay, now if you redo the same variational analysis, also this guy has a structure like this. But this time, the minimum is that A is equals 0.5, and the corresponding energy is negative 0.5, which is smaller than the previous estimate that was 0.42. Which tells you that this is a better variational argument. So the second variational estimate was better than the first one. Actually, if you actually plug this function into the radius Schrodinger equation, you discover that the second variational ansatz is in fact an exact solution. What do I mean? I mean that if you take the second variational ansatz, let's call it R bar, and I do my TR R bar plus UR R bar, there's no centrifugal term, we are in S wave. This is going to be proportional. Actually, this is going to be the ground state energy we just computed to R bar. So in fact, this is an exact solution. This is one of the luckiest situations in which not only by variational ansatz we have found a better solution, we actually found the optimal solution, which is basically telling me that we know the ground state just as much as we could know the ground state of the harmonic oscillator analytically, while the excited states are very complicated. The same thing happens for the hydrogen atom. The ground state is simple to obtain. The excited states are more complicated. And in this course, we are only concerned, we're looking at the hydrogen atom. So this is a fairly short lecture, And in some sense, it closes the discussion of atomic physics. I'm not going to go into much further detail. I'm only going to comment on a few things. We neglected quite a lot of physics. So let me list things we neglected in exposing this theory. Well, first of all, we neglected the mass of the proton. We consider the mass of the proton to be infinite. Well, this can be straightforwardly adjusted by going to relative coordinates, and you get 1 per mil corrections. So the corrections here are small, but exactly calculable. But there are many other things we neglected. First of all, we neglected the size of the proton. This is a small effect because the proton is 5 orders of magnitude smaller than the size of the atom. But we also neglected all sorts of magnetic interaction. Why did we include Coulombic interaction but neglected magnetic interactions? You know, after all, electromagnetism is a one single theory. The reason is that typically magnetic interactions are driven by at least the orbital, you know, what kind of magnetic are we talking about? That the electron is moving with a velocity. The nucleus has a magnetic field because it has a magnetic moment. So we have an electron moving with velocity in a magnetic field of the nucleus. So I have a magnetic field which I draw like this of my nucleus, and I have an electron now in a classical picture that is moving in a magnetic field. This would generate a Lorentz force. Now the force, classically, the force that the electron would satisfy in appropriate units would be proportional to the velocity times external vector with a magnetic field divided by the velocity of light and the charge. Now, as long as the velocity of the electron is small compared to the velocity of light, this would be very, 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 very small. Now, is the velocity of the electron small compared to the velocity of light? Well, we can answer this question because we can go back to the typical average kinetic energy. And from the average kinetic energy multiplying by twice the mass of the electron, we get an average square momentum from which you get the average square electron velocity. And this is actually showing you that, in fact, you expect this to be extremely small corrections. There are other effects associated with the intrinsic magnetic moment of the electron interacting with the nucleus magnetic moment. And also these are relativistic effects in some sense. These are small effects, and we have neglected. So all these effects are called hyperfine structure of the hydrogen atom. And basically what they imply is that, remember, you know, if you have, for instance, a p state, in the p states there are three different m states, right? Because it's L equal 1 corresponds to m equal 1, 0, and -1. So there are 3 energy levels that are the same, they're completely degenerate. But if you switch if you take into account of the effect of the magnetic moment, of course, whether the electron is circulating with, you know, this component of the angular momentum or in the opposite direction, it will experience opposite forces from the nucleus, and so you will get the splitting of these energy levels. But this energy splitting here are very small. And all of these effects in general will produce a spectrum which has major bars. So these are the excitation levels. But if you look at them very carefully, even experimentally, you'll discover that they have a little bit of a structure. So in addition to major, large absorption energies you can get from photons, you should be able also to resolve small energy absorption by photons. And all this material was an intense subject of investigation last century, in the first half of the last century. And all of this extremely complex phenomenology was reproduced to death, so to say, by quantum mechanics. So none of this experimental information was left unexplained. And this contributed enormously to establishing quantum mechanics as a leading theory, as the fundamental theory for matter in the quantum scale, in the microscopic scale. Okay, for the next lecture, we're going to move on and talk about molecules. Goodbye.